Thank you very much, Adam, and thank you for the invitation to this workshop. Definitely something that it holds very closely to my heart to how can we really improve this area of benchmarking and create a community around that can think together about the challenges and how to overcome them. As Adam said, I work for Siemens. I'm located in Berkeley, in California, and I'm heading a group of advanced manufacturing automation that deals with advanced robotics and artificial intelligence, how these two can enable more flexible robotics. And the work that I'm gonna present you in a second, I would like to also give a lot of credit to the main authors, Gerrit, Toby, also Eugene. Gary and Toby were interns during a long period of time in our office, and Eugene is one of our senior research scientists. And also all our collaborators, all the videos that you will see, the cool robots moving, hopefully, they're also in collaboration with UC Berkeley, mainly the lab from Peter Avil and Sergey Levin. So just jumping into the topic, as you know, there is a paradigm shift in controls for machine autonomy on how do we enable this flexibility, how do we make these robots learn new tasks without necessarily programming every motion. And the traditional robotic control pipeline, which consists on observation, state estimation, modeling, planning, and different levels of control, is being also transformed slightly to, or a lot, to address this end-to-end learning setups as the one that you have seen, for example, from this robot farm from Google. We like to think about ourselves in the middle between these two worlds of from 100% model-based to 100% data-driven. But we also think that this is a continuum. It's not just a binary decision. Either you turn it on or off. You can have different levels of autonomy and flexibility, and also the use of data-driven methods versus more traditional approaches. But even in this continuum, the question arises on how do you compare different algorithms, right? And what you're seeing in the video, hopefully if all of these guys render, robots trying to do different types of tasks, some of them failing, some of them succeeding, right? And at the end, what we want to see is how do we define this kind of artifacts, this kind of benchmarks, to be able to compare different algorithms. And I will talk about all these different benchmarks in a second. This is part of our gear assembly. This is something that we call factory model. And this is the famous by now NIST board. So we didn't need benchmarks, right? And I was also very happy to see that in Joao's presentation that somehow the gears appeared there, and that has been also very, had a lot of utilization in different labs around the world. But what we really believe is that benchmarks accelerate innovation. Everybody knows about ImageNet and how it has really served as a catalyst for deep learning boom in perception. And the question is, can we have an ImageNet moment in robotics, right? Because that was really what really accelerated the deployment of deep learning to computer vision. Now, why benchmarking in robotics, right? And this has been also discussed in several other presentations. So every paper reports a different experiment, and it's unclear what the contribution is. We need to be able to reproduce results better, and we need to be able to say we are this good, right? But what are we really benchmarking in robotics? And that goes back to also some of the conversations, some of the other workshops that I have seen in past conference on what is really robotics, right? Are we really just doing pose estimation benchmarking? Are we benchmarking the grasping capabilities, the insertion capabilities, the mechanical precision of the hardware, the overall system design, all of this together? And when we talk about specifically in robot learning, it's very different if you want to benchmark and if you want to learn for control versus learning for perception, right? The performance really depends on the physical effects. And it's also not realistic to expect that every lab in the world have the same hardware and the same physical environment. And it's a really big difference between simulation. There was a really good workshop yesterday on sim to real and the real world, right? Particularly when you talk about realistic tasks that wanna find its way into manufacturing. There are things like the OpenAI Gym, where you have environments, not just agents, but these are mostly academic scenarios, right? Not suitable for manufacturing. As much as I like to see dinosaurs learn how to play soccer, as in some papers, it is also limited in applicability because of the simulation, right? It's only in simulation. So can we design a physical benchmark environment? And that was what motivated us more than 4 years ago to create this robot learning challenge, where you can see the link on the top. And we decided to create a benchmark, a physical benchmark, where researchers around the world can simply 3D print the parts and try out this assembly. It consists on different parts, 2 peg in the hole problems with these pegs that can move, and different gears, the 3 ones that you see, and another one with a different pattern, so you don't overfit to a specific solution. And everything moves, right? So it gets very tricky. It's not easy to hard code the motions, because at the end, you need to find your way into when you're assembling the gears. And this has been, as I said, used by different labs in the world. For example, this is a paper from, I believe, DeepMind, and this is another paper from the academic world. We were very happy also with the reception of this challenge and how different labs around the world have used it. But it's not that one benchmark fits all, right? It's not a silver bullet. So we also have, I'm gonna report some of the results with a different kind of setup where things can also fall, and that may be also different and useful for different setups. But these two still are very lab oriented, right? One can claim that, okay, this is not a realistic manufacturing problem. And then we were also very happy to partner with NIST and do a lot of tests and work around the NIST board. But even there, that's also a set of kind of an artificial environment. And the next step, what we are pushing currently, is also using a realistic through-hole electronics assembly from a real product. And that will also be kind of complement the full picture of benchmarks. Now, when we give these benchmarks around, or people want to tackle our challenges, it's not easy to just say, okay, report me your results, right? Because what we want is to answer different questions, and we would really want to take a look in the details, because different setups are, it's difficult to say this is better than the other one, right? Because it's usually, the answer is, it depends. It depends on the conditions. So the first question that we always ask is, does it work, right? As you see on the videos before, right? You saw that some robotic actions work and some others not. Also, how robust is to perturbations in terms, for example, of lighting, right? Are you controlling the light or not for your perception algorithms? How well does it generalize, right? What if I place the components, if I move the board slightly, or the components that you're trying to pick, at what cost, right? It's very different if you use a Intel RealSense camera for $300 versus for example, a Photoneo 15,000 LiDAR, right? It's very, you get a very different output, but also that's what you pay for, right? And also what cost in terms of data, how much data you need for training, and how much time does it take if you are learning to learn the policy that finally works, and also how to set up and for another person to run it, right? These are the least academic questions, but if we want to transfer this into real manufacturing, that will be also very important. And what are the limitations? And as I said, for example, in the following video, it's really the way that we made it work was also using a $10,000 camera, which produces these really nice point clouds, as you can see here, right? So we want to know also the setup. That's equally important as the algorithms that you are using. So now I want to, now that hopefully I have drilled the topic more on why do we need benchmarks, I want to show you some examples on how do we use these benchmarks in our research. The first one is about our work in residual reinforcement learning. And for that, we want to solve this insertion in this benchmark where the blocks, let me pause this for a second. The blocks can be in any arbitrary position. And the goal is to insert one of these blocks in the middle without making the others fall down. As I said, the tricky part here is that the blocks can fall down. In the gear example, the setup is kind of fixed. So you could have luck and find your way through if you do some kind of a spiral motion, but here it's more tricky to do the exploration phase. As you can see, just a simple hand engineer controller would not work because it will feel that it's touching something. It will not know how to learn the motion of pushing things around, and it will just fail to accomplish the task. So these are results that we published in the past on can we also use this traditional control with reinforcement learning, that's what we call residual RL, to solve this kind of problem. Only use reinforcement learning where it makes sense, when the contact dynamics, when you have contacts to model that are difficult to model. And as you have seen, you can see in a second, so after many hours, I think 3 hours of real world training, the system finally even here, one important thing is to report is, first of all, the time that it took to learn your setup, how many cameras you use, your robot, what is your physical layout, and also how did you restart the system, right? Because if you find a way, if it's 3 hours of real world training, but you have a way to automate this learning, that's very interesting, versus what we did, that is basically one of our students resetting the experiment for many hours, right? Every time that the robot fails, the blocks will fall down and then you have to restart it again. A little bit more also, so now that we were comfortable on using the residual reinforcement learning in our setup, we also use it using one of the NIST boards. And this was actually very cool that they have a USB, because usually what we use in reinforcement learning to define the rewards is the final position of the objects that you're assembling. But if you have currents, you can also use that as a reward. So that was also very useful. And as I said, usually the state-of-the-art reinforcement learning, assembling this kind of task will take training time 12 to 24 hours, and we reduce the time to 3 hours. But 3 hours is still a long time. So we continued our research also using the NIST board in the area of meta learning. Basically, meta learning means learning to learn, and we have 2-step processes where we first have a long meta training following by a fast adaptation. And we leverage a lot simulation to reduce this extensive training time. And if we use 4 days of training in simulation and 5 million simulated robots, but at the end we can, in around 20 minutes, learn a new task. And I want to show you also some of our results. This is our robot setup when we have 2 cameras, one to detect where the connectors are, and another one to also detect how have you grasped the part. And this is very easy because you have different features. So you're just showing the connector to the camera so the camera can see. And as you can see here in this video, after around 20 rollouts, the system gets it perfect. So right now you are 60% accurate in the last 5 rollouts. And then once you get to 20, it's all the time successful. And we use the same kind of training to also assemble the gears that you see here in the board, and just fast forwarding for the sake of time. And at the end, Again, after 20 rollouts, it learns and is all the time successful. And finally, what we wanted also is to use the same policy to also train in the board. And I think I'm over time, right, Adam? But as you can see here, this is also another benchmark.
You're
so
okay.
Just to conclude, this is my last slide. We learned that having multiple benchmarks help. It also helps to really differentiate if this is just you assemble it by luck or if you are robust enough, if you can really, your policies, what you have learned can generalize. It's important to clearly define what is your scenario, what is your hardware and instrumentation, and what are the different modules that you are using, and what are you really benchmarking, right? What are your contribution? Is this on the grasping or is on the computer vision part of things? And also measure things that are not obvious, right? Like engineering effort, lines of code, and flexibility. So that's it. If you have any questions or ideas on how can we create the next version of our benchmarks, we are happy to discuss that.
Thank you very much. Yeah, I think the idea of quantifying the amount of learning, that is a very interesting problem. And you kind of presented two cases, one that is measured in hours, let's say, and another that is the kind of number of attempts before reaching competency. Are there other kind of simplified measures like that we could apply to learning to help characterize it?
Well, one of the biggest one is also the training time, right? How long does it take to learn the different policies? At the end, with this, for example, this meta learning, what you do is instead of having a traditional, like a data set where you fit your model, you have a set of data sets. And this data set, so the robot has to figure out in real time which one fits the problem at hand. So it's very interesting also to see when this will break, right? Because this also, it depends on how well can you simulate the problem in your simulation and how much can it generalize. All the tasks that we have seen here, they are kind of similar. It's just putting an object into insert it, but we haven't tested if the same policy can also really generalize to something completely different. So training time, also to your point, is something very important. Also, do you need human intervention? That was also something that would be very interesting. If you can restart your problem automatically versus if you need a person for X amount of time to restart the problem while you are learning.
Human intervention can basically increase the cost of learning, if you want to frame it that way.
Yeah, also, do you need safety also plays a role, right? Is the robot, can you ensure that this will do just the motions that are safe, or do you need to constrain it somehow?
Okay.
Okay, thank you very much. And if you have any other questions or interest, you can always reach out.
Actually, James, did you want to ask a question?
Yeah, I wanted some more detail on the blue blocks of the benchmark. It looked like there was something going on in between the blocks and that lower surface. Was there anything other than a flat surface?
Yes, so that's a very good question. So we decided that for simplifying and also to make it a little bit more manageable, we added a magnet. So that's a very good catch. So there is a magnet below each of these blocks to still make them, they will fall, but they will not fall that easily to just, if we push them a little bit.
Oh, okay. Thanks for clarifying. Thanks for your talk as well.
Yeah. And the interesting thing is also we have tested with magnets and without. And it's interesting also to see that the policies that the robot learn are different in both cases. So it learns to be more gentle when things can really fall, and a little bit more aggressive when you have the magnets.
That's interesting.
But very good point, Jim, and question.
Thanks.